So, this is the second hour from the first lecture of cluster analysis. We will continue with the second type of clustering, which is hierarchical structure clustering. The hierarchical clustering uses the distance matrix in order as the clustering criteria. So it clusters objects based on their distance or the distance between them. And in this method, we do not need to identify the number of clusters, such as in k-means or k-medoids, when we decide how many clusters do you want, which is the number of k. In this case, we only need a termination condition, when to stop combining or um, objects into clusters. In this method, we have two types. We have the Agnes method and we have the Diana method. And they have the same concept, but um, uh, they are opposite. The way they approach the objects is actually opposite. In the Agnes, we start by having each object as a cluster by itself, and we end up by having all objects combined in one cluster. In Diana, all in one cluster, and then we end up with the ending condition or the stopping condition will be when all of each object will have its own cluster. So this is the Agnes, the agglomerative nesting. It was introduced in the 1990s. Well, you don't need to know when was it introduced. You just need to know the algorithm. It is implemented in statistical packages such as Plus. It uses a method of counting distance between objects called the single link. We will look into it in a minute. And it also uses the dissimilarity matrix. And its approach is to merge nodes or merge objects that have the least dissimilarity. So the least, which means that they have the most similarity, they are merged together. And it actually goes on in non-descending fashion until we end up having all objects in one single cluster. The dendrogram is a clustering diagram that we viewed in a minute, but now we're just talking about it's a tree-like structure of representing clusters, and it decomposes the data into several levels of partitions. In this way, if we want to know which data objects or which objects belong to the same cluster, we cut the dendrogram in the desired level, and we will see which objects belong to which cluster by seeing them by seeing the connected components. So if we cut it here, we see that P4 is representing a cluster, P2 and P3 representing a cluster, and P1 is a cluster by itself. If we cut it here, we will see that P2, P3, and P4 are one cluster, and P1 is one cluster. The second type of hierarchical clustering, which is the Diana, and it was also introduced in the 1990s. It's also implemented in statistical analysis packages as Plus, but it is actually the inverse order of Agnes. Eventually, applying this algorithm, we will have each cluster or each object to be a cluster of its own. To calculate the distance between clusters, we mentioned the single link. There are other ways, such as the complete link, the average, the centroids, the medioids. The single link is actually the smallest, is defined as the smallest distance between an element in one cluster and an element in another cluster. So the smallest distance between one element, two elements in different clusters. The complete link is actually the largest distance between an element in one cluster and an element in another cluster. The average is the average distance between an element in one cluster and an element in another cluster. The centroid is the distance between the centroids of two clusters. So we're actually measuring the distance between the centroid from each cluster. And the medioid is the distance between the two medioids of two clusters. And we explained what medioids are earlier. Third approach or a third method for clustering is the density-based clustering. The density-based clustering is actually a method that identify clusters by density, by the number of points that are close to each other. Density معناها كثافة. So clustering based on density is actually looking into points that are connected based on their density, based on their proximity. The major features of this approach is that we can discover clusters of arbitrary shape. It can handle noise very well compared to the other approach. We can do that in a one scan of data set. We don't need to do multiple scans. And in order for it to work, we will need to properly identify the density parameters in order to have a termination condition. So the density parameters are the termination condition, and we will see what density parameters are in a minute. There are many examples of density-based clustering methods, such as the dbScan and optics, DELCLU, and we have Click, but we will have or we will study dbScan as an example of this type. So what is the basic concept of density-based clustering? There are two main parameters that we need to set up for the algorithm to work. We have epsilon and we have the minimum points. The epsilon is the radius of the maximum radius of the neighborhood. So if we define a neighborhood using a circle, the epsilon is the radius of this circle. The minimum points is the minimum number of points. Points here means objects in the epsilon neighborhood of that point. So we will set up a required number of objects or points to be in the neighborhood. So we'll have a minimum requirement. Okay. Now, if we have a point that is P, that is directly density reachable from a point that is Q, okay, with regard to epsilon and the minimum points, the minimum points requirement. In this case, we say that P is density or directly density reachable because P will belong to the points within the identified epsilon of Q, and a core point condition is satisfied. So what does that mean? It means that when we identify or when we define the algorithm, we will define an epsilon, which is the radius. In this case, we identify the radius to be 1 centimeter. And we identify the minimum number of points to be 5. Now, we consider Q to be a core point if it satisfied both. So if we draw a circle with an epsilon of 1 centimeter, and within this circle we can find a minimum of 5 points, then we can say that Q is actually a core point. We say that P is reachable if P is actually within the radius of or within the identified neighborhood of Q. In this case, we say that P is reachable or belongs to the Q neighborhood. Okay. Now, density reachable, a point P is directly density reachable from P2. So this is P, and we say that P is directly reachable from P2 because it satisfies the condition. They identify the minimum points to be 7, okay, and these are the neighborhoods based on epsilon. So if P is reachable from P2, also P2 is directly reachable from P1, and Q is P1 is directly reachable from P1. In this case, we call the P2, P1, and Q to be a chain. So in this case, this is considered to be a chain, which means that P is density reachable from Q. So you can reach P from Q because there is a chain of points that can get me to P, and all of these points have neighborhoods that satisfy the minimum points condition. Now, density reachable, we say that a point P is density reachable from a point Q with regards to epsilon and minimum points if there is a chain of points P1 until Pn that can get or can connect P and Q together. In this case, we say that P is density reachable. Density connected, a point P is density connected to a point Q with regards to epsilon and minimum points if there is a point O that both P and Q are density reachable from O with regards to epsilon and minimum points. When we say with regards to epsilon and minimum points, it means that it's always satisfying the conditions of epsilon and minimum points. So we have, this is P and this is Q. We say that P and Q are density connected if we can find a point here, in this case O, that is directly connected to P and directly connected to Q. Q here should be in this place. It's actually seems there's a mistake here. Now let's talk about density-based spatial clustering of applications with noise, which is the DB-scan algorithm in particular. It relies on density-based notion of cluster, what we just explained, the idea of density-based clustering, where a cluster is defined as a maximum or a maximal set of density connected points. Now, if we have density connected points, we call them as, or we identify them as one cluster. So this algorithm, the DB-scan, discovers clusters of arbitrary shape in spatial databases with noise. So it's very effective in identifying outliers. We have three types of points when we are dealing with a DB-scan algorithm. We have a border point, we have a core point, and we have an outlier. Now, if we identify epsilon, in this case 1 centimeter, and we identify minimum number of points to be 5, we can draw, or if we want to identify our clusters, we start by drawing circles that satisfy the epsilon and minimum points condition that should have minimum 5 points. Now in this case here we have 1, 2, 3, 4, 5, 6 actually. There are six points or 6 objects, and these 6 objects, all of them satisfy or within the epsilon shape of 1 centimeter. Now this point here, which is the center of this neighborhood, is called a core point. Now a point that if you draw the shape, in this case the circle, and it satisfies the 1 centimeter epsilon, however it does not satisfy the minimum points condition, which is 5 here, like here, it's the only point in the neighborhood, this point is called an outlier. A point that when you draw the shape of epsilon, which is 1 centimeter, and minimum points, it actually satisfies the epsilon, but does not satisfy the minimum points, is called a border point. So this is a border point because it does not satisfy the minimum number of points condition. Okay. So we identified the three notions of border point, core point, and outlier point. And here we have epsilon 1 unit and minimum points to be 5. So given epsilon and minimum points, categorize the objects into three exclusive groups. So if we call a point a core point if it has more than a specified number of points, so it satisfies minimum points within the epsilon, okay? And these are points that are at the interior of the cluster. So these points are considered to be part of the cluster. A border point has fewer than minimum points with epsilon, but is in the neighborhood of a core point. So it's close to a core point. In this case, we call it a border point. Now, let's go through the algorithm, the steps of the algorithm. Arbitrarily select a point P. So we start by selecting a point P. And we will be retrieving all points that are density reachable from P. Of course, we will be satisfying epsilon and minimum points. If P is a core point, meaning that it satisfies the minimum points condition, then we form a cluster. If P is a border point, in this case, no points are density reachable from P, and DB scan visits the next point in the data set. So it's in this case, P is considered a border point, so it's not there. A cluster is not formed. We continue the process until all of the points have been processed. So this is the first step. Check epsilon neighborhood of P. So this is P, and we will draw the epsilon, and the minimum points is 5. So here 1, 2, 3, 4, 5. Okay, satisfied. If P has less than minimum points neighborhood, then mark P as outlier and continue with the next object. Otherwise, mark P as processed and put all the neighbors in cluster C. So P in this case is actually satisfying the condition of minimum points as 5. Then we will be identifying this is the first cluster, C1. Check the unprocessed objects in C. So now we start looking into the objects in C. If no core objects, return C. So in this case, if there are no core objects, we did not find other core objects. In this case, we return C, meaning a cluster. Otherwise, randomly pick up one core object, P1, mark P1 as processed, and put all unprocessed neighbors of P in cluster C. So we will identify P1 within the cluster. So now we will be looking at P1 as a potential core point. We continue doing that, scanning, identifying the neighborhood, identifying points, seeing or deciding whether the point is a core point or a border point. If it's a core point, we add it to the cluster. We identify it as a cluster. If it's not, then we check whether it is a border point. If it's a border point, then it belongs to the cluster of the point that we just processed. And we continue the process, we continue the scanning until we end up scanning all the points in the data set. Now, this is an example of epsilon equal 10, minimum points is 4, and this is the original points. And based on the colors, the green here are core points, the blues are border points, and outliers are red points. These are interesting examples of the DB scan and how it is sensitive to the parameters, to the epsilon and the minimum number of points. Also, this is an online demo for DBScan, very interesting visualization of DBScan. We could probably look at it and see how does it change when we change epsilon or change the minimum number of points, and how it affects the number of clusters identified in the data set. Okay, this is it for this lecture, and next week, inshallah, we will continue with the other types of clustering. Thank you very much.